right, lesson 3, location and arrangement of electrons within the atom. So yesterday we focused on the nucleus and its properties, the nucleons and their properties. And today we're going to focus on the electrons because electrons are what control the chemical behavior of a particular element. Okay. Atoms may have one or more electron shells. The closer the shell is to the nucleus, the less energy that the shell has. And of course, the further away from the nucleus, the more energy. The furthest one would have the most energy. And that just has to do with proximity. It takes less energy to make a small circle than it does to make the big circle. You can determine how many electron shells are going to be in an atom based on the period number. So if it's in the first period, there's 1 shell. If it's in the second period, there's 2 shells. Third period, 3 shells, so on and so forth. The electrons in the electron shells can be represented in a couple of ways. On the left side of the screen here, I have 2-8-1. And there are versions of the periodic table, not the one that I passed out, but there are a lot of them available that generally have this information on it for every element that's there. It kind of gives you their electron configuration. This 2-8-1 that is here basically just means that sodium is in the third period, so it has 3 shells. There are 2 electrons in the first shell. There are 8 electrons in the second shell, and there's 1 electron in the third. This one that's out here in the third, the highest energy level, is what we refer to as the valence electron. That's the one that can be lost or gained in order to initiate bonding. Bohr models are also pretty useful at identifying the electrons in a shell. A Bohr model has the nucleus, and then we have each of these orbitals, or I'm sorry, these orbits, if it's a Bohr model. And it's showing that here's 2 in the first shell, then here's 8 in the second, and then there's 1 in the last. So Bohr models we did in Chem 1, this written out configuration like this, we did not do. So this is a newer way of looking at it. There is a maximum number of electrons in these electron shells. Every shell is going to have a maximum amount. We refer to that maximum amount as N, like a variable X or Y or whatever, but we refer to it as N. The maximum number of electrons in a shell will be referred to as N for the variable. So that means if N is equal to 1, it's the first shell. If there's N is equal to 3, it means the third shell. To calculate the maximum number of electrons in the shell, you use the formula 2n squared. So you take the shell number n, square it, and then multiply by 2. And this will tell you how many electrons are available in this particular shell. So for example, what would be the maximum number of electrons found in the third shell of an atom? So that would be a sample type question. If it's the third shell of the atom, then n is equal to 3. So if n is 3, 2 multiplied by 3 squared, which would be 2 times 9, is equal to 18 electrons. The maximum number that we could have in our third shell is 18. Just because there is a maximum amount, that doesn't mean that everything has to be always filled. We do have partially filled or incomplete shells that have electrons less than the maximum number. For example, one way to look at this would be which of the following elements has a completely filled third shell. And so if we look at these options, we have aluminum, 283. So its third shell has 3 electrons. Calcium, 2882. Its third shell has 8. Argon, 288. 8 has in the third shell. And then krypton, 2818 and 8. If we look at the third shell, if we know that 3 is in, so we just calculated on the last slide, 2 times 3 squared is 18, then the third shell has to have 18 electrons. The only option here that has a third shell with 18 electrons is krypton. Very simple. So this would be completely filled. This would be not completely filled or a partially filled, incomplete. Hey, about what? It is a noble gas. But if we follow, this is quantum, okay? It's a little more than Bohr. This Granted, I agree with you. It has an octet in its outer shell, which is what we look for stability. But in this particular case, it's stable. Absolutely. It's got that octet. So if I were going to look for stability, I'd look in my valence electrons, which would be the last shell, and see if it has 8. So calcium doesn't have it. So it's going to be unstable. But these do. The third shell, according to quantum physics, the math part of it, goes with that formula. I don't know what's happening. Blinky. Okay. This is just the answer if you want to just skip that. Krypton was the only choice with 18. In order for us to understand the next concept, which would be reading spectrometry or spectral lines and spectrometry, we have to go back and revisit ground state, excited state, and spectral lines. We talked about ground state and excited state and absorption and emission models in Chem 1. Spectral lines, though, is a Chem 2 topic. Important to note that atoms are stable when all their electrons are in the ground state. So they are the most stable when all electrons contained within the atom are in the ground state. Ground state would be the electron configuration that you find on a periodic table. And like I said, I may go ahead and I may try to find y'all one that's good quality that I can print with those configurations on it, so you can have access to that. But this would be the one that was found on the periodic table. That's what always is provided if you have a periodic table with electron configuration information. Electrons always go from they enter the lowest energy level first and then go to the highest. That's the off-bow principle. We enter the lowest one available to us. It is important to note that if you have electrons in their ground state, in order for them to move to a different state or their excited state, we have to absorb energy to make that happen. The energy that we absorb is in the form of a photon, which is a particle of light. A photon is also defined as a quanta of energy. It's like a little package of energy. And not every photon has the same package of energy. Some have more than others. So they are variable. Excited state. This is an electron configuration that's different than the periodic table, and and we're going to do some practice questions, hopefully at the end of class, that you'll see where we have, an element that has its ground state configuration and its excited state. You'll see that there is a variance. There's a difference. The electron has moved from one level to a higher level. Energy is high, so unstable. The lower the energy, the more stable. The higher the energy, the more unstable. The electrons, though, they've already absorbed this energy. That energy is going to have to be released in order for the electron to travel back to its ground state. And when it does that, a spectrum of colors is produced when we go from excited to ground. Because we understand the electromagnetic spectrum and we can relate different colors of the electromagnetic spectrum, excuse me, with energy, frequency, and wavelength, we can then correlate that to the movement of the electrons, and then we can start to understand the energies of the various electrons within the atom. With this spectrum that is produced, there's something called spectral lines. These are going to be produced from the energy released by the excited electrons as they return to their ground state. These are generally referred to as the fingerprints of an element because each element has its own unique pattern of colors at specific wavelengths. So you can identify an unknown substance based on its spectrum. One of the ways that when we look out into space and people say, well, Venus, the atmosphere is made of sulfuric acid. Ways that we determine that are generally through the diffusion of spectral lines. We measure the light coming back from those stars or planets and so forth. And because of this spectrum that we know to be true here, we can pretty closely guess the composition of things that we really can't contact just by looking at the spectrum that is released. This is an example of an electromagnetic or a spectral lines or whatever. This is for helium. Every element has one. This is just an example here. You can see there's like a fine red line, pinkish there, a pretty thick yellow one. Here's like a green. There's some blues moving down into our purples. But if we know that this is helium, then when we see this spectrum, we can identify helium as one of the elements present. All right. One of the things that led us to even looking into the chemical behaviors and the development of atomic models were flame tests. A flame test, we did them back in Chem 1. It's a lab procedure where you take compounds that contain metallic ions and then you heat it, and you'll notice that it can produces different flame colors. If we had the capabilities, we could use a spectroscope in order to look at the light produced by that flame. And it would separate our light into various color patterns or spectrums. Once we have that information, we can use that spectral chart to identify the element. Oh, sorry. I thought there was another line. Okay. There's really nothing to write down on this slide. This is just if we were to look at white light, and if we were to look through a spectroscope to identify the spectral lines, we would see what we see here at the top. There are emission and absorption spectrums. The emission spectrums are the ones that are traditionally used. That's what I've seen most. Some of you will end up, especially if you major in chemistry, you'll have to take a course called mass spectrometry, and this is literally all you do for a semester. I cried a lot, but I got through. It's not as easy as it looked like it would have been from the outside. But anyway, you look at these emission spectrums or absorption spectrums, and we can identify based on the wavelengths and the colors that are present what type of element it is. This happens to be hydrogen. So we can see from there. All right. So electrons and atomic emission spectra. We did it. All right, we're going to try a virtual lab. I'm gonna be honest, I went through about 5 minutes of it. I didn't have any major issues. So I'm going to put it in our Google Classroom. We're going to try it and see how it works. It looked good.